to Learning Machines seminars at RISE. Today's speaker is Maria Bånkestad, who is a researcher at RISE and a PhD candidate supervised by Thomas Schön at Uppsala University. Maria works on machine learning for physics and chemistry, and has been working on Bayesian uncertainty quantification and stochastic processes. So please, Maria, the floor is yours.
Hello, I'm Maria. Now Olof already introduced me, but today I will talk a bit about variational inference, and I will talk a bit about what it is, why we use it, and how we can use it a bit. So here's just a flash of examples that variational inference actually has been used for the last years, and it is used in everything where in this research where they like try to find this exoplanet, and in the COVID research, and also when you have this really huge like topic models. And also in like this model-based reinforcement learning. And in general, if you have like big problems with the big data and you're interested in like uncertainty, variational inference is a tool you can use. So that's the main thing you can use it for. It's where it outperforms other models. So when we talk about variational inference, it is exactly the same as variational Bayes. So we use Bayesian inference. So using Bayesian inference, we instead of just model parameters in our model, we model them as probability distribution, and we don't call them parameters anymore, but we call them latent variables when they have this probability distribution. And we will instead call them Z here, but yeah. So you can model when you have a probability distribution of your parameters, you have like this prior over the data. And in Bayesian inference, then you have your likelihood describing your data, giving the latent variables. And when you combine these two, you get the posterior. So this is pretty much what you want when you do Bayesian inference. You want to learn about your data by looking at you want to learn your latent variable by looking at observations. But this, I don't know, integral or this expression can be really tricky to derive. And it's really tricky because it's usually consists of this integral in many dimensions, and with so it's usually intractable. So this is where Bayesian variational inference comes in, because in variational inference we try to approximate this tricky posterior, which we call the posterior, with a simple, nice distribution, Q of Z instead. So we have this family of nice distribution. And instead of doing like this sampling techniques or something that you usually do, you translate it to an optimization problem where you try to find the best distribution among this family of distribution that approximate your posterior. So by transforming it from a sampling problem to an optimization problem, it lets us scale this to big data. So let's put variational inference in perspective and relate it to other models. So variational inference here in the middle can do two things. It can, as we said, infer the posterior, but it's also a tool for maximize the evidence, which is the probability distribution of our data. It's what we want to optimize when we want to optimize parameters in our probabilistic model. So instead of Monte Carlo sampling, we can use variational inference for to approximate posterior. And another model that also try to optimize the evidence in this Bayesian model is expectation maximization. I will come back to this a bit later, so I'll just give an overview here. So now we'll talk a bit about these latent variable models. So if you have observations, and when you do Bayesian inference, you want to model some probability distribution of this observation. And this can be like really tricky to do, because sometimes you want to model a probability distribution over, for example, molecules, or you want to model a probability distribution of pictures. So then you can introduce this. Oh yeah, I was supposed to say here, we talk about P of X here, but we can actually also talk about P of Y given X, and it's the same thing. When you talk about P of Y, you model P of Y given X, you model the probability distribution over Y, and you look at X as parameters that are fixed, that we don't change during optimization. So everything I say also, you can also think of this will hold. So, but I will talk about P of X here just to make it simple. But again, we add this latent variable to give some structure to the model. And latent variable are all those variables that you cannot observe. It can be like this, as I said before, parameters, but in other fields, latent variables can also be like, if you have, say, in psychology, you can think of latent variable as intelligence or personality, like something that exists, but you cannot really observe it, and it's difficult to, yeah, but maybe it's still something you want to include in your model. Or in economics, you can think of quality of life, or like conservatism. They can be seen as latent variable. But if we are more technical, a latent variable can also be something what you use in probabilistic dimensionality reduction. Like you have this X, and you try to represent it by something in a smaller, like in a lower dimension. And in more general, maybe you have some like really complicated distribution, but you think you can like make it more tractable by making this hierarchical structure with simpler distributions. So from our latent variable models, we can do, there are two things we want from a model, as I said before. So it's a tool to make more tractable models, Bayesian models. One example here is, for example, the Gaussian mixture model. And here, the latent variable are the mixing component, which is modeled as a categorical distribution. So one Gaussian distribution is a simple model, but by adding this latent categorical distribution, we can create really complex distribution of it. So then it's a tool to make more complicated or give structure to complicated distribution. But we can also just use it to infer the posterior. We want the posterior. We want the probability of, we want to know the intelligence, or we want our weights in our Bayesian linear regression or something like that. Or we want when we do that dimensionality reduction, we want the variable in lower dimension. That's what we want. So there are two things we can want here. And when we train this latent variable model, we want to optimize the evidence, which is the model of the observations where we have integrated out the latent variables, because these are not observed. So we need to integrate them out before we can train it. But this integral is in general intractable. And yeah, it's tractable in some cases when we have like these conjugate priors yeah, you can solve this, but in general, for these larger problems, it's like impossible to solve this. But we can, by using variational inference, create a lower bound of the evidence. And we do that by approximating the posterior with a simpler one. So I will again, like I talked about variational inference before, just go through it again. That we have this nice family that we want to choose from, and we try to optimize the parameters of this variational distribution to get the best one. And here the phi is the parameter of the variational distribution, and theta is the parameters of our model. So we have two different sets of parameters here. So just give an example. If we try to find if our family of distribution are just like this Gaussian distribution, this like could be a good fit. But if we try to make this family of distribution larger, for example, take a mixture of this Gaussian distribution, we can get an even more better fit for this. So we get so this like both give an approximation of the posterior at the same time that we get a tractable way to optimize the evidence by using this lower bound. But so how do we construct this lower bound? So we will use this variational approximation, and we want to add it to the model. So what we do is we just both multiply it and divide by it. So we haven't really done anything. And then we see that this is just the same as the expectation. So in Bayesian inference, like integral over something, it's the same as taking the expectation. And now we can use the Jensen's inequality. So now we get and put the log inside the expectation instead. So here we have moved the log inside the expectation. And now it's less or equal to, so it's not equal to the expectation anymore, but it's less than equal. So we have a lower bound. It's lower than the evidence. And this is called the ELBO, or the lower bound, evidence lower bound. Another way to write ELBO, which I won't derive here, is taking the evidence that we want to optimize, that's our goal, minus the KL divergence between the approximated posterior and the true posterior. And the KL divergence measures how similar two distributions are. So if they are really similar, the KL divergence will be 0. And actually you can see that by letting the KL divergence be 0, the ELBO is equal to the log evidence. So we have a perfect fit with this approximation. So yeah, we can also write it as the evidence is equal to the ELBO plus the KL divergence. And
Maria?
Yeah?
We have a question in the chat.
Ah.
Can you take it now?
Yeah. If it's not too quick.
Yeah. When we say family of distributions, do we mean 1, the same distribution but with different choices of parameters, or 2, larger distribution family such as exponential family or distributions like normal, etc.?
I think in the most common case, we select like a structure of the distribution, optimize the parameters. Yeah, that's like the family of distribution. But I think there probably are research of like selecting among different types also. I'm sure. I haven't seen it, but you can just ask questions anytime. It's fine. And I try to answer it. And so I just made this graph of the ELBO, and now we try to optimize this this ELBO. So first, we try to optimize them by taking the variational parameters. These are not the model parameters. So this will actually decrease the KL divergence. We get a better approximation of the posterior. And we also increased the ELBO, but the evidence stays the same. We haven't done anything to the evidence. But then we optimized the model parameters. And now, the model evidence will increase, and the ELBO will also increase probably, but the KL divergence will probably become larger again, because we want it as small as possible. And this is because we don't have the same model anymore. We have a new model with a new posterior, so now the approximation isn't as good anymore. And so we do this iteratively. You can see it as like the variational distribution tries to chase the true posterior during optimization. And eventually this will converge, hopefully. So by taking the gradient of the ELBO, we can take it with respect to the parameters also. Then this expression becomes quite simple actually, because then we can just take a Monte Carlo sample of this variational family. Okay, this is not that important, but we can take a sample here and this expression becomes simple. The tricky about optimizing these models is taking the gradient with respect to the variational parameters. Because here, you remember, we had the expectation with respect to the variational distribution, and we try to take the gradient also at the same time. And here is where here is a bit where the research is right now, like how to do this in the best way. And there are many tricks here, like the reparameterization tricks and other that can fix this. I will not go into that now, but we can just say that this is the tricky problem, but the libraries out there solve this for you. So, but this is difficult, yeah. And traditional method, maybe you heard about coordinate descent or CAVI. They do this, but they have to do this like iteratively, like they first optimize the one and the other, and they have to work like with these really simple variational distributions. And it doesn't scale to big data. But modern methods, they can optimize this both simultaneously at the same time. And they also use stochastic gradient descent instead. So we can scale it to big data by mini batching and stuff. So now we know a bit more. We can go back to this slide again. So we had variational inference in the center. And we had Monte Carlo sampling here, which is another method to get the posterior distribution. And Monte Carlo sampling actually gives you the exact posterior distribution, but it can be slow and doesn't scale to big data. But if you have a small data set and you want to infer the posterior for that, and it's important that it is correct, then you should use Monte Carlo and not variational inference. Expectation maximization is really similar to variational inference too, but here you need to have a tractable posterior. But if you know the posterior and how it looks like, then you can use expectation maximization. But yeah, if you have big data, and if you have no idea what your posterior looks like, you should use variational inference. So now I will talk about one type of variational inference that has become popular lately, and it's amortized variational inference. So in general, when you have a latent variable model, you have one latent variable for every data point you have in your data set. So yeah, so when you scale this to big data, you can imagine how many different latent variables you get. And maybe the latent variable is distributed as a normal distribution. Then you both have to model the mean of that and the variance to be able to get this distribution over the latent variable. So that becomes even more things you have to learn. So here's the trick here is that instead of seeing this as latent variables is separate latent variables, you create a function that maps the data points to the latent variable here. So yeah, and this whole procedure is called amortized variational inference. So this function can, for example, be a neural network or yeah, something else. It can be anything really, but yeah, typically a neural network. And this allows us to scale these models to big data, because now you don't need to model every single latent variable. So you can use this mapping instead. And the most famous example of using amortized variational inference is the variational autoencoder. So in a variational autoencoder, you have this latent variable model that you want to learn, where every single latent variable maps to an observation. And you have this joint distribution. And you create a model. Now we talk about the model, not the posterior. The model where every like this latent variable maps to this X through a neural network. So you sample from, the model is like you sample from your prior and you let that sample go through the neural network, and then you get your output, your model of your observation. And since we want to scale this for big data, so you can imagine like we have this really complex model, latent variable model, and therefore the posterior of course will be intractable. It's like impossible to find it. And here variational inference comes in to solve this. So here, instead of getting the true posterior, we create an approximation of the posterior by using amortized variational inference. And it's important to know that this is an approximation. It would be better to get a real distribution of the latent variable. But since we want to scale to big data, we use amortized variational inference here to try to make this problem suitable for big data. And generally in a variational autoencoder, you let your latent variable be Gaussian. And so you map your input to a mean of a Gaussian and the variance of a Gaussian. So the function in the amortized variational inference consists of two functions. And yeah, and then yeah, you can sample from that normal distribution. So we have here the posterior, or sometimes called the encoder in a variational autoencoder. But that is just an approximation of the posterior. And then we have the likelihood, which it maps the prior to the observed variables, which is our latent variable model here. It's also called a decoder, because it decodes, and yeah. So here like is a big picture of the variational autoencoder when you train it. So you model your distribution of your posterior, you sample from it, and you add it to you use that during training to as an input to your generative model. But then, yeah, this is just during training, because then you remember that the expectations was taking with respect to the variational posterior and not like the prior. So here you use the variational posterior during training to create your objective, your ELBO. And so, but after we are done training, we have actually just used this posterior as a tool to create this really complex, deep latent variable model, because otherwise we couldn't get like otherwise it would be intractable to train it. So the posteriors was actually just used as a tool to be able to train this model. So we actually, we throw almost everything away, and we have our generative model in the end. That was what we wanted. Yeah, sometimes you want the latent variable in the middle to something else, but in general, if you want a generative model, everything else is just a tool to create this model or train this model. So now you can use this model to sample whatever you train it on. And nowadays there are a lot of tools to do this, use variational inference for your models. I know that TensorFlow just released this TensorFlow probability. It's actually built on an old library called Edward, which they have developed it even further, and included it into TensorFlow. I think it's really good. I haven't tried it. I mostly worked in Pyro, and it uses PyTorch to create Bayesian inference models. And it's built mostly with the aim of using variational inference. But you can also use like sampling, like Monte Carlo sampling and other stuff here. And then we have two libraries here, STAND and PyMC3. They are they are built for Monte Carlo sampling more, like these sampling techniques. But they have now also included variational inference in their like package. Both STAN and PyMC3 have that. So you can, they are not built on Python. It's like the C++ library. I don't know what PyMC3 is. So with that said, what I want you to remember after this is that variational inference, it enables you to do Bayesian inference on big data. And it's also a tool to approximate this Bayesian posterior. And at the same time, it's also a tool to create this lower bound of the evidence, which you get when you have a latent variable model. And with these new model libraries, we can choose any variational distribution as we want. Nowadays, it's really common to like use a normalizing flow, for example, or this really like complicated variational distribution, since there's nothing, you cannot really overfit when you train your posterior, when you train your approximate posterior. There's nothing like overfitting there. You want this to be as complex as possible, but still tractable. So this is where like the modern research in variational inference lays. It's like trying to create this really flexible approximate posterior distribution. And it's also a lot about combining like Monte Carlo sampling with variational inference to create even better approximate posteriors. If you're interested, you can read about it. But you can also use it for big data nowadays with these new good libraries like TensorFlow and Py and Pyro. Yeah, thank you.
Thank you, Maria. Do we have any questions for the speaker? Could you mention some examples where you've applied variational inference yourself?
I mostly used it for Gaussian processes, actually, because when you want to scale it to larger data sets, you can use variational inference to like create this sparse version of the Gaussian processes. And you can also use it with other types of likelihood, other types of noise models in the Gaussian process. So you don't need to use like Gaussian noise. And so it's also a tool to use Gaussian process for classification, because then you can add other likelihoods. Yeah, that's where I've been using it the most, actually.
So maybe I have a question regarding the use of on big data. So do you think, I mean, like, how is the performance in general of variational inference on larger data sets if you compare this with like some other methods in general? And or maybe another way of saying it would be like, what kind of big data problems would be more appropriate for if we have like this set of tools, and variational inference is one of them.
I didn't really understand.
Sorry, I can repeat the question. So I mean, when you talk about like the use of I mean these methods on big data, do you have any recommendation or like any kind of like guidance of like for which kind of problems? I mean, like if I have like, I mean, one is that like I have a big data, but I have like some idea of like the underlying like process that has generated that data, or one is that is completely blind. I mean, and then there are like some other methods that you can use. So do you have any suggestions or like guidance or?
I don't really know. I can say what I think. So if you're interested in like this, if you have some idea of how this process, like you probably want to create a Bayesian model somehow if you have some idea how the process behind the data worked. And I guess if you want uncertainty and a probability, a model with uncertainty, there's not much else out there, I guess. But it's still, even if I say it scales to big data, it can be really tricky to optimize with variational inference still. So I shall not say that it's super easy. I don't have any recommendation, I'm sorry, more than that.
I mean, like, I've worked with like, Markovskian Monte Carlo methods. And I mean, they're like, you see like, that with the high dimensional problem, usually, I mean, it's kind of very hard to reach like, that station distribution or like even near sometimes.
No, it's probably better to try it variational inference actually, if it's really, because it can take a long time to reach.
Yeah. Thanks.
Then I can recommend, if you have worked with the Monte Carlo method, I think variational inference is worth trying, but you have to know that it's an approximation still. So yeah.
I mean, I'm during my PhD, I used that like for tree-based models, and like these were like so space was larger, so and was tree within tree reconciliation. So and it was quite hard to use Markovskian Monte Carlo. I mean, like you ran it for many days sometime, and like
man, I understand. But there are also methods that combine Monte Carlo and variational inference. So you use variational inference to get a good what do you call it? Proposal distribution, for example, and then you can take some Monte Carlo steps in the end to, if you really want the true posterior, you can mix and match these two methods too. So
that's a good idea, I think, because the proposal is kind of I mean, we use very simple proposal at that time, so
it's a good starting point. It goes faster with the Monte Carlo.
Thank you.
Okay, so then we should thank Maria for this talk. Next week, we'll have Professor Tuomas Virtanen visiting from Tampere University, where he's the leader of the audio research group. So welcome back next Thursday. And thank you again, Maria.
Thank you.
Thank you very much. Thank you.
Thank you.
Bye.
Bye.